You remember yesterday. You know what you had for breakfast. You recall conversations, faces, moments, but you can't remember tomorrow. You can't recall what you'll have for breakfast next week, or what conversation you'll have an hour from now. The past is fixed in your mind. The future is blank. Why? A glass falls and shatters, but shattered glass never spontaneously reassembles and leaps back onto the table. Coffee cools down. It never heats itself back up. We age. We never grow younger. Time flows in one direction, forward, always forward. Yet the fundamental laws of physics are almost perfectly time-symmetric. Newton's equations, Maxwell's equations, even Einstein's relativity. They work the same whether time runs forward or backward. So where does time's arrow come from? Why does the universe have a direction? Why can we remember the past but not the future? This is the arrow of time. And it's one of the deepest puzzles in all of physics. The arrow of time is the one-way direction, or asymmetry of time. At the fundamental level, physics doesn't distinguish between past and future. If you filmed two billiard balls colliding and played the video backward, the physics would look perfectly normal. The laws governing the collision work identically in both directions. But if you filmed a wine glass falling and shattering, then played it backward, showing fragments leaping off the floor and assembling into a perfect glass, it would look absurd, impossible. Yet the microscopic physics of every atom in that glass is time-symmetric. So why does the macroscopic world have such a strong sense of direction? This is not just philosophical. The arrow of time is deeply connected to entropy, cosmology, quantum mechanics, and even consciousness. Understanding it means understanding why we exist in a universe where cause precedes effect, where memory captures the past, and where the future remains unknown. The thermodynamic arrow. Entropy always increases. The most fundamental arrow of time comes from thermodynamics. The second law of thermodynamics states that, in an isolated system, entropy tends to increase with time. Entropy is often described as disorder, but more precisely, it's a measure of the number of microscopic configurations that correspond to the same macroscopic state. A shattered glass has vastly more possible arrangements of atoms than an intact glass. High entropy means many possibilities. Low entropy means few. The second law says entropy never decreases in isolated systems. When you drop a glass, it shatters. Entropy increases. The reverse never happens because there's only one way for the atoms to be arranged as an intact glass, but trillions of ways for them to be scattered as fragments. The universe naturally evolves toward more probable states, and high entropy states are overwhelmingly more probable. This gives time its direction. The thermodynamic arrow of time is provided by the second law, which says that as a system advances through time, it becomes more statistically disordered. You can tell which direction time flows by watching entropy. If entropy increases, time moves forward. If it decreased, time would be running backward. But we never see that in macroscopic systems. Consider a simple example. Heat exchange between two objects. If you place a hot object next to a cold one, heat flows from hot to cold until they reach the same temperature, thermal equilibrium. The net change in entropy is positive because the cold object gains more entropy than the hot object loses. This process is irreversible. Heat never spontaneously flows from cold to hot. That would decrease entropy, violating the second law. Time's arrow points from hot to cold, from ordered to disordered, from low entropy to high entropy. But here's the puzzle. Why was entropy low in the first place? The second law tells us entropy increases, but it doesn't explain why entropy started low. If the universe always increases in entropy, it must have begun in an incredibly low entropy state. and that requires explanation. The cosmological arrow. The universe had a beginning. The universe is expanding. Galaxies are moving apart. If you run the expansion backward, you reach a point where everything was compressed into an incredibly hot, dense state, the Big Bang. This happened about 13.8 billion years ago. The early universe had extremely low entropy. Matter and energy were distributed almost uniformly, with only tiny fluctuations. Those fluctuations grew into galaxies, stars, and planets. But the initial state was remarkably smooth and ordered. Why? This is called the past hypothesis, or the problem of initial conditions. The cosmological arrow of time, the fact that the universe has a definite beginning and expands in one direction, is linked to the thermodynamic arrow. Some physicists argue that the cosmological arrow is the reason for both the thermodynamic arrow and the quantum arrow of time. As the universe expands, it creates more room for entropy to grow. Stars form, burn fuel, produce heat and light, and eventually collapse or explode. Black holes form, which have enormous entropy. The universe gradually fills up with disorder. If the universe eventually stops expanding and starts contracting, a scenario known as the Big Crunch would time reverse. Some theories suggest entropy might decrease in a contracting universe, as distant particles that were correlated at the Big Bang come back into contact, revealing hidden order. In this scenario, the arrow of time would reverse. Broken glasses would reassemble. We'd grow younger. But this is speculative, and current observations suggest the universe will expand forever, driven by dark energy. If so, entropy will increase indefinitely, and time's arrow will never flip. The psychological arrow. Why we remember the past. You remember yesterday. You don't remember tomorrow. This seems obvious, but it's deeply connected to the thermodynamic arrow. Memory is a physical process. When you form a memory, your brain creates a record, a pattern of neural connections, chemical changes, electrical activity. This requires energy and increases entropy in your brain and surroundings. Crucially, memory formation is irreversible. Once a memory is encoded, it can fade or be distorted, but it doesn't spontaneously unencode and return your brain to its previous state. The arrow of memory, remembering the past, not the future, aligns with the thermodynamic arrow. Both point in the same direction because both are entropy-driven processes. Neuroscience research shows that remembering the past and imagining the future rely on similar cognitive and neural processes. The constructive episodic simulation hypothesis suggests that when you imagine the future, your brain recombines elements of past experiences. You simulate possible futures based on what you remember. But you can't truly remember the future because memory requires a causal trace, a physical record left by past events. The future hasn't left any traces yet. It's not determined. So memory is inherently backward-looking. Some philosophers and physicists ask, why don't we remember the future? In a time-symmetric universe, both past and future exist equally. This is the block universe view in relativity. Yet our subjective experience is asymmetric. One answer: memories are correlations between your brain state and past events. Entropy increases in the direction of time, where correlations decrease. We form memories of the past because the past was lower entropy and more ordered, leaving clear causal traces. The future is higher entropy and less predictable, so we can't form memories of it, only predictions. Evolution shaped us to remember the past and use that information to affect the future. This makes biological sense. Knowing what worked before helps you survive. If you remembered the future, you wouldn't need to plan or decide. Everything would already be fixed. The fact that we remember the past and not the future is both a consequence of thermodynamics and an evolutionary adaptation. Other arrows: radiation, quantum, and causality. There are other arrows of time beyond thermodynamics. The electromagnetic arrow. Radiation spreads outward from sources. A light bulb emits photons in all directions. You never see photons converging spontaneously onto a bulb and being absorbed. This is time asymmetric. The equations of electromagnetism allow both retarded, outgoing, and advanced, incoming waves. But we only observe retarded waves. Why? It's linked to boundary conditions and the expansion of the universe. Classical electrodynamics can be understood as a time asymmetric theory when cosmological considerations are taken into account. The quantum arrow. In quantum mechanics, measurement seems to introduce irreversibility. Before measurement, a quantum system exists in a superposition of states. After measurement, it collapses to one state. This process is time asymmetric. You can't unmeasure a system and return it to superposition. However, some interpretations of quantum mechanics, like many worlds, deny true collapse, suggesting the asymmetry is observer-dependent. Recent work in quantum cosmology explores fundamental time asymmetries in quantum thermodynamics. Decoherence, the process by which quantum systems lose coherence due to interaction with the environment, is also irreversible and contributes to the arrow of time. The causal arrow. Cause precedes effect. We never see effects preceding causes. In our reference frame, you break an egg, then scramble it. The scrambling doesn't cause the breaking. This seems obvious, but it's actually a manifestation of the thermodynamic and psychological arrows. Our sense of causation is built on the assumption that low-entropy, ordered, states precede high-entropy, disordered states. Interestingly, quantum mechanics complicates causality. Experiments with entangled particles show correlations that don't depend on which measurement happens first. Some physicists propose time-symmetric formulations of quantum mechanics using both initial and final conditions. In such theories, time asymmetries arise not from the laws themselves, but from differences between initial and final boundary conditions. A special initial condition, low entropy, and a final condition of indifference, high entropy, would be sufficient to explain observed time asymmetries. Is the arrow of time fundamental or emergent? This is the big question. Is time's directionality built into the fabric of reality, or does it emerge from statistical regularities and initial conditions? Most physicists favor the emergent view. The fundamental laws, quantum mechanics, relativity, are time-symmetric or nearly so. The arrow of time emerges from the second law of thermodynamics, which is statistical, not fundamental. Entropy increases because high-entropy states are vastly more numerous, not because there's a law forbidding entropy decrease. But this raises a deeper question. Why did the universe start in a low-entropy state? If entropy increase is just statistics, low entropy should be rare. Yet the Big Bang was incredibly low entropy. This is sometimes called the entropy problem in cosmology. Possible answers: boundary condition. The low entropy beginning is just a brute fact, a boundary condition of the universe. We don't know why, but it's necessary to explain everything else. Anthropic principle. Only low-entropy universes can produce complex structures like stars, planets, and life. We exist in such a universe because we couldn't exist in a high-entropy one. If there's a multiverse, most universes are high-entropy and boring, but we're in a rare low-entropy one. Deeper law. Maybe there's a deeper theory, quantum gravity, string theory, or something unknown, that explains why the universe began with low entropy. Perhaps the initial state wasn't a choice, but a necessity. Cyclic cosmology. Some models propose the universe goes through cycles of expansion and contraction. Entropy might reset at each bounce, or there might be mechanisms that drive entropy down during contraction. This is highly speculative. Time-symmetric universes. Could they exist? Some physicists have explored whether a completely time-symmetric universe, with symmetric initial and final conditions, could be consistent with our experience. In such a universe, entropy would be low at both ends, beginning and end, and high in the middle. Observers in the middle would experience an arrow of time pointing toward higher entropy, regardless of whether they're before or after the midpoint. Both directions would feel like forward to observers in those eras. This is bizarre, but not ruled out. It would mean time's arrow is relative, not absolute. Future civilizations, if the universe contracts, might remember what we call the future and not remember what we call the past. However, this requires very special boundary conditions. Both beginning and end must be low entropy. Why would both ends be fine-tuned? This seems even more mysterious than just explaining one low entropy beginning. Practical implications. Why the arrow matters. The arrow of time isn't just abstract physics, it's why technology works. Engines, computers, and life itself rely on thermodynamic gradients, differences in energy and order. When you charge a battery, you're decreasing its entropy locally by increasing entropy elsewhere, in the power plant, the environment. The arrow of time is why batteries discharge, why fuel burns, why we age. It's also why computation is irreversible. Erasing information increases entropy. Landauer's principle states that erasing one bit of information generates a minimum amount of heat. This links information, thermodynamics, and the arrow of time. It's why computers heat up. It's why Maxwell's demon, a hypothetical being that could decrease entropy by sorting molecules, can't exist. It would need to erase information, generating entropy in the process. The arrow of time even affects artificial intelligence. Neural networks learn by adjusting weights based on past data. They don't learn backwards. Their training is time-directional. If we ever build time-reversible computers, quantum computers can, in principle, run processes backward. They might challenge our intuitions about learning and memory. Living with time's arrow. We are creatures of time. We age. We remember. We plan. We regret the past and hope for the future. These experiences are shaped by the arrow of time. If time were symmetric, you'd remember the future as vividly as the past. There'd be no suspense, no uncertainty, no growth. Life would be fundamentally different, or perhaps impossible. The arrow of time gives life meaning. It's why stories have beginnings, middles, and ends, why actions have consequences, why decisions matter. If you could undo every mistake by reversing time, nothing would matter. The irreversibility of time is what makes existence profound. And yet, the arrow might not be absolute. At the quantum level, processes can run backward. Particles can be described by time-symmetric equations. In black holes, time and space swap roles. Inside the event horizon, you inevitably move toward the singularity, just as outside, you inevitably move toward the future. Time's nature is stranger than everyday experience suggests. So why do we remember the past and not the future? Because we live in a universe that started with low entropy and is evolving toward high entropy. Because memory is a physical process that requires irreversible changes in the brain. Because evolution shaped us to use past information to navigate future possibilities. The arrow of time is thermodynamic, cosmological, psychological, and biological. It's the thread connecting the Big Bang to your morning coffee cooling on the table. It's why you're reading this sentence now, not earlier or later in some timeless sense. You exist in time's flow, and time flows only one way. Forward, always forward.